Alright, so last video we went over some basics and we kind of left the circuit in a complicated manner with a bunch of crazy numbers and fractions all over the place. So what I've done since then is I've simplified the circuit to make it into one single loop, and the way I did that was, remember over here on the left side, this used to be it used to be two elements. It was a capacitor in parallel with an inductor. So I combined those two elements, and remember, whenever you have two parallel impedances, it's product over sum. So you take the impedance of both of them, multiply them, and then divide by their sum. So remember, the impedance of the capacitor was 1 over j omega c. The impedance of the inductor is j omega l. So I would recommend you do the same mathematics to simplify the circuit and see if you get the same answer as I did right here. And I will show you right now the work that I did. So here's the work that I did. So if you want to pause this and see if you get to the same results. Now this is only for the capacitor in parallel with the inductor, because that was the most complicated part. The rest of the math was pretty simple. It's just dividing fractions, putting them into calculator and such. So a couple things here that might not be very intuitive to you, that's not just straight regular old mathematics. A couple of rules that I used were dealing with this imaginary number j. So one of the rules is 1 over j is equal to negative j. Now remember, j, so here's the proof for that. Remember, j is the square root of negative 1. So if you have 1 over the square root of negative 1, if we were to multiply the top and the bottom by that same radical, we would get the square root of negative 1 over negative 1, which is equal to the negative square root of negative 1, which is equal to negative j. Let's see, what's another one that I used here? J squared is equal to negative 1. And that's because if you have the square root of negative 1 and you square this, basically the square and the radical cancel each other out and you get negative 1. So whenever you're doing math with these imaginary numbers, those are some rules that can help you. So So our next thing we need to do is we need to solve for the two values that we originally wanted to solve for. One of them was this current right here going in this direction that we're just calling I, and I think we want it as a function of time, so I of t. And we wanted the voltage across this parallel combination over here. And that was, let's see what that was. V1 of t. So right now we're doing the A part of the problem. So V1 of t. It's starting to look a little messy. Let me clean that up a little bit. V1 of t, calling that positive and that negative. So, the way I figured we would do this is, like I said, I would do a KVL equation, a loop equation, and the reason is because using that we can solve for that voltage and that current conveniently at the same time. So let's see here. We also need to know our voltage, which is stated in the problem. So the voltage is 100 cosine of omega t volts. So 100 cosine of omega t, and remember omega is 2 pi f, where f is 60 hertz. So that's our sinusoidal voltage waveform. So if you remember from Ohm's law, solving for current is pretty simple. It's voltage divided by impedance. But in this case we're not just dealing with a resistor, so the math turns out to be a little complex. So, like I said, I'm going to start with a KVL equation where we already said the sum of the loop voltages should equal 0. So, V1 of t. Oh, before I get into that, here's another thing. As you can see, we're going to end up dividing a bunch of numbers in complex form with j's in them, the imaginary number, and real parts. And we're going to have a cosine in there. It's not very fun math to do that. So the easiest way, what we want to do is we want to convert all of the numbers into one similar format. So you can either convert them into polar form or rectangular form. So polar form is basically whenever you have a sinusoidal wave, you have an amplitude, and I usually put it in parentheses, and then you have an angle, and then you have your theta, so which is your phase shift. So if we wanted to put this cosine statement into polar form, we can see that amplitude is 100 right here. The phase shift is 0 because there's no phase shift here. If there was a phase shift, it would be 2 pi 60t minus 45 degrees or something like that. So we could call this 100 angle 0. But then what we need to do is we need to put all these other statements in polar form too. Now if we prefer, we could put this in rectangular form, but as you'll see, in my opinion, the math comes out easier to do it in polar form. So that's what I'm going to do. So, like we said, we have 100 angle 0. That's our voltage. Plus our voltage across this resistor, which remember we're going to call this plus, minus, plus, minus, plus, minus here. Now our voltage across that resistor is going to be our current times that resistance. So current I which for simplification I'm not going to put the I of t in here, times our resistance. So let's see, let's make sure we're doing this right. We called this a positive voltage here, leaving the positive. So remember, this resistor, the signs are the opposite direction as this voltage source, so we need to call that one a negative. Same thing with the inductor. Now that's why I already put the impedance here in that form, so we don't have to calculate the impedance as we're going along with this equation. So it'll be minus I times J 600 minus I times the negative J, so that'll become a plus 13.3 times 10 to the 6. And then over here we are going in the opposite direction again, because now we're entering the negative and leaving the positive. And the reason we're doing that is because that's the way the problem defined the voltage. So this one will be a plus. Plus I times J 3.77. So we just did a full loop of all the voltages. Remember, the voltage law says that sum should all equal 0. So now our problem is we have one thing in polar, the rest in rectangular. And you know what? I'm going to go back on what I said here. Since there's only one thing in polar, and since we're adding everything up, it's going to be easier to do everything in rectangular. So to do this in rectangular form, what you would do is you have to look at an axis, and we call this the real axis, and this is the imaginary axis. And we have a vector on here where we know our magnitude is 100 and our angle from the real axis is 0. So this is the angle right here. That would be about 45 degrees. If that angle was 45 degrees, then this is how we would draw the line. Since our angle is 0, our line is just straight on this real axis with a magnitude of 100. So what does that tell us? That tells us there's no component of this voltage source that has an imaginary portion. So there's no J's involved. So in rectangular coordinates, we can just call that 100 volts. Because there's no J. So first of all, I'm not sure, in rectangular form you have a complex number. It's always going to be A plus J times B, where A is your real part and B is your imaginary part. As we just showed here, since the angle is 0, there is no imaginary part. Therefore, we can call this just 100 in rectangular coordinates. So, let's go like this. Let's say 100. Now I'm going to group everything together. All the real parts I'm going to put together. and all the imaginary parts I'm going to put together, which is already done for us here actually. So instead of rewriting all this out, I'm simply going to change what I already wrote and make that 100. So now we want to solve for I, the current. So we need to get I by itself. So as you can see, I is in all these terms except for the 100, so we just need to do a little bit of algebra here. So we can say I times 10 minus J 600 plus J 13.3 times 10 to the 6 plus J 3.77 . So let's see here, I took an I out of everything. Looks like I missed a negative sign there. Negative 10, negative, positive, positive. And we're going to bring the 100 over to the other side of the equation, so we'll get a negative 100. So now we can say I is equal to negative 100 divided by all of this. So now what we need to do is we need to combine all of the real and the imaginary in that denominator. So down here we have 600. I'm going to go over to the calculator here. So we have 600 plus 13.3 times 10 to the negative 6 plus 3.77. So basically, it looks to me like this 13.3 times 10 to the negative 6 factor is not going to matter much at all. So we could have just ignored it. See? We don't want to carry out to that many figures, so I'm just going to call this 603.77. So this is equal to negative 100 divided by negative 10 Whoa, you know what, I just noticed a mistake here. Okay, so let's go back up to here. Sorry about that. So remember, this 100 corresponds to that voltage source, this 10 corresponds to that resistor, the 600 is that inductor. Now 13.3 times 10 to the 6 here, we got that here. We have that here. For some reason I made this a -6 down here at the bottom. That might have just been a little mistake. So let's go ahead and say the opposite is true here of what I estimated earlier. Whenever we thought this was to the -6 power, we were going to say it wasn't going to matter. Now it looks like the other two aren't going to matter. So I'm going to call this denominator here -10 plus J 13.3 times 10 to the 6. That number is so big that the other two aren't going to affect it at all, unless you carry out to, say, 4 decimal places or so. Okay, so we have our value for current, but it's in rectangular coordinates still. Remember, we ultimately want to get back to a function of time. So the easiest way to do that is to convert the rectangular coordinates to polar coordinates, because you can directly look at the polar coordinates and the polar form, I should say, and you can make a cosine function out of that. So we could just go ahead and transform the denominator and numerator right now, so that's what I'm going to do. So I'm going to say the top is -100 there's no j involved, so we can call that angle 0, or you can, okay, so let me show you something. Angle 0, this is the same thing as saying 100 angle 180 degrees. As you can think about our axis over here. Remember whenever we said it was 100 over here? Well, if it's -100, it'll be 180 degrees out of phase. So, so let's call this, just like I said, 100 angle 180 and then the denominator, that's where we need to use those little vector diagrams, because this one will actually come into play. So if we make a little coordinate system here like we did before, we look at this complex number and we can see that the real part is -10, and the imaginary part is 13.3 times 10 to the 6th. So that means here's our vector. So if we want to have this in polar form, we need this angle right here, and we need the magnitude of the line. So for this angle, we can use a little trigonometry. What I would do is I'd find this first angle, this inside angle first. So that angle is, let's see, actually before we find the angle, it's easier to find the magnitude. So the magnitude is going to be, using Pythagorean's theorem, the square root of 10 squared plus 13.3 times 10 to the 6th squared. So that's showing you right there. Now look at this little 10 squared here. That's going to be almost nothing. So that's showing us that our real part is very, very insignificant compared to our imaginary part. Well, we could have seen that up here. This is definitely not out of scale, not in scale. If we're 10 here and 13.36 times 10 to the 6th, then our vector in reality is going to look more like very, very, that angle should be very close to 90 degrees, that angle that we find. So as I said, that will be our magnitude, and then our angle will be any cosine trick that you want to use. We can say cosine theta is adjacent over hypotenuse. So cosine of, let's call that theta there. So cosine theta is adjacent, so that's 10 over hypotenuse is that magnitude that we're about to calculate. So then theta, that angle right there, is going to be inverse cosine of 10 over the magnitude. But remember, we don't want theta, we want this other angle that I'm going to call phi. So phi is 180 degrees minus theta. So let's go back over to the calculator and find that magnitude real quick. You know what, just for simplicity, since I know that 100 is going to be so insignificant, I'm just going to call that magnitude just that imaginary part. Now if you want to get into more details, you can, but I don't want to waste your time punching numbers into a calculator. So I'm going to call this 13.3 times 10 to the 6th, and I'm going to call that angle 0. So whenever you divide these polar functions like this, the amplitudes you divide like you would anything, and the angles you subtract them. So our final, almost final answer will be 100 divided by 13.3 times 10 to the 6th angle 180 degrees. So let's see here. Let's see how we can I'll just go ahead and punch that in. 100 divided by 13.3 times 10 to the 6. Oh, of course, it gave me a nice format. So 1, 2, 3, 4, 5, 6. So that's 7.52 times 10 to the negative 6. 7.52 times 10 to the, did we say negative 6? Yeah. To the negative 6, angle 180 degrees. So now, to just put this in a time-dependent function, our answer is going to be, let me clear some of this space off here. Our answer for I of t will be 7.52 times 10 to the negative 6 cosine, and then we just look at our original function. Cosine of omega t minus 180 degrees. Or you can say plus, it's the same thing whenever it's 180. Let's see, what else did I... You know what, I found another mistake actually. Remember whenever we did that little diagram and we said that most of this denominator was going to be imaginary because of this 13.3? We should have put 90 degrees right there. Because we were saying the angle was going to essentially be this right here, because our vector was going to be just straight up like this. So in that case, we're subtracting. Remember, you subtract the angles whenever you divide them. So our final answer will be somewhere around 90 degrees. So we're essentially saying, remember our voltage didn't have a phase shift here. We're essentially saying that our current is 90 degrees out of phase with our voltage. So let's think about that for a second. Looking at our circuit here, let's look at a better one. Looking at our circuit here, look at all these values. We have something to the first order of magnitude, 3 point something. We have 10, we have 600, and then we have to the 6th power. So if you have a purely capacitive load, then your current is going to lead your voltage by 90 degrees. So we can essentially, now remember, I made some approximations here because I didn't want to round to the 4th decimal place. I'm basically saying that our load is purely capacitive because our capacitance impedance is to the power of 6, while everything else is to the power of 2 or lower. So that's a good sanity check right there. You can look at your circuit and say, well, is it mostly capacitance, or is it half capacitance and half inductance, or is it half resistance and half capacitance? Then it would be 45 degrees. So A, we have our answer for our current. Now you could also, what we like to do, I wouldn't call this times 10 to the negative 6. I would say 7.52 cosine omega t plus 90 degrees microamps. And I'd write 2 pi 60 for omega, because our frequency didn't change. So we got the current. What's the other part of A? The voltage V1 of t. So since I've taken so much time on this, I'm not going to get too far in that. But just think, I'm going to let you handle that part, and just think of Ohm's law. So if you know the current, there's only one current. It's the same current going through everything. If you know the current, you can and you know the impedance here, you can calculate the voltage. Now you have to keep in mind though that this is not a voltage drop. This is a voltage rise. So you will want to multiply this by -1. And you do not want to multiply the current in this form, in this sinusoidal form. You want to take that vector that we already, the polar form, this guy right here, 7.52 times 10 to the negative 6, angle 90, times the polar form of this impedance. Well, the polar form of this impedance, this is purely reactance. It's purely imaginary impedance. So you know that angle is going to be 90 degrees because it's in the positive form. So this is going to be 3.77 angle 90 degrees. So you're going to multiply this, what I just said, angle 90 degrees, times this in polar form, times -1. Then you're going to use the same methods that we just used to bring it back into a time-dependent function for the voltage. So you should be able to handle that. So B says, for the source frequency 60 Hertz, calculate active and reactive power supplied by the source. So not sure how much you know about active and reactive power. So what we usually like to talk, so apparent power is called S, and that is equal to your real power, P, plus J, which is the imaginary number again, times your reactive power. So here's how I would challenge you to answer that one. Active and reactive. Active power is your real power. P is real active. Q is reactive, so it's imaginary. And reactive. So, I'm sure you remember from, if you know anything about circuits, you know how to find power. It's so P equals V times I. Well, it's the same thing for total apparent power, your complex power, S. You can multiply your voltage, but now you're going to say, you know, S equals, I'm not even going to try to write it out, to be honest with you. I'll tell you what to do is, you find the voltage. You have the voltage. It's given to you. It's this 100 cosine 2 pi 60t. Put that in polar form, which we did. You have the current, which is right here. Put that in polar form, which we did. You multiply the voltage times the current. So you're going to multiply two polar forms, and then you're going to put it back into rectangular format. Whenever you put it into rectangular format, you're automatically going to see that the real part is your active power, and your imaginary part is your reactive power. So that's that. You can easily do that. That's just mathematics. So determine the source frequency. We're on C now. Determine the source frequency so that the current I of t is in phase with the voltage V2 of t. What is this frequency called? So, as we said, at 60 hertz, remember these impedances of these reactive components, they're dependent on the frequency. And we just found that at 60 hertz, we can basically call this a purely capacitive load, which means that our angle, our phase shift, is 90 degrees positive. If it was a purely inductive load, it would be negative 90 degrees. If it's a purely real or resistive load, then our angle will be 0. So you have to find the frequency that will make these values either cancel each other out or be extremely small compared to the 10 ohm resistance. So that's going to be quite a bit of mathematics, honestly. So what you could do is you're going to have to leave the impedances instead of solving them out in numbers like we did for the actual values. You're going to have to leave an F in there for frequency. So, you know, you'll have, say, example 13.3 F. It won't be 13.3, but it'll be something F. So whenever you come out with all these equations like we just did, everything will have an F in it. And you're going to solve for the value that will make the J's go away, basically. Or solve for the value, same thing, where the angle is equal to 0. So I'll let you think about that since we're about out of time, but if you want to focus more on that, we can. I know how to solve it. I'm just telling you, all it is algebra. It's long, extensive algebra. Okay, source frequency, like we just said, so that it's in phase. What is this frequency called? That frequency is called the resonance frequency. Resonance. I'll write that out. Resonance frequency. The definition of resonance frequency is the frequency that will make the amplitude as high as possible. and that amplitude comes whenever everything is real, whenever there's nothing imaginary. And like I just said, if there's nothing imaginary, then your angle will be 0, so your amplitude will be the highest. So determine the source frequency so that the power supplied by the source is 0. So again, you're going to have to come up with an equation for the power of the source, like we just said. So whenever you do C, never mind, forget that. So you're going to come up with an equation or a function for I of t, but it's going to be dependent on the frequency. And you're going to come up with a equation for V1 of t, source frequency. You already have the equation for the source frequency. It's given in the problem statement. This right here, 100 cosine of omega t, or 100 cosine of 2 pi f t. So you have the voltage, you have the current, you don't know the F, but you know the voltage times the current is equal to 0, right? So solve for F. And you'll have to play around with, it's probably not going to work out just doing it cosine times cosine. You're going to want to do it, try it in polar form and try it in rectangular form and see which way gives you the answer easier. So I think that's a good start for you on this. I hope you've seen polar coordinates or polar form and rectangular form before. So let me know if you have any other questions, and I hope this was helpful for you.